Greetings and welcome. Today in this video we're looking at graphing parabolas using the kind of quote-unquote slopes technique. Now these aren't technically tangent slopes of the parabola at any point. They're technically more secant lines that pass through the parabola at 2 points, but it is a way that we can somewhat quickly find more points on our parabola without doing a lot of additional work. So for this first problem, what I've got here is my quadratic equation. I found the vertex by using the formula negative b over 2a, right? So b was the negative 6, a was the 1, and found 3 was the x-coordinate of my vertex. To find the y-coordinate, I plugged that back into the function, right, for both of the x's, simplified, and found negative 1 was the y-coordinate. Now, just some quick analysis. So for this problem, A was 1, B was negative 6, and C was 8, right? A was the 1 hiding in front of the x there. So this 1 tells me that this is a regularly shaped parabola. All right, so let's, using that fact, what I'm going to do when I graph this, let's see, I think I've got a grid we can use right here. So let's plot our vertex here. We've got 3, negative 1, so over 1, 2, 3, down 1, right there is our vertex. And based off of the value of a, I can determine a couple things. Since a is equal to 1, it tells me it's a regular shape. And since a is positive, it tells me that it opens upward. Alright, and by opens up, I mean the parabola itself. The two arrows are looking upward, that the inner part of the parabola is pointing up, right? So using this slopes trick, I told you in a previous video that the slope, quote-unquote, of a regular parabola is going to be the following, where its consecutive points can be found by going up 1. Let me actually choose darker color here, maybe some orange. So if I go up 1 over 1, that will give me a point on the parabola, right? So 1 and 1. If I go up 3 over 1, that'll give me another point on the parabola. And then if I go up 5 over 1, I think that takes me all the way up to 8. That will give me yet another point on the parabola. And then from here I could go up 7 or 9, and then 11, then 13. And I could find all sorts of points on the parabola using the fact that these consecutive odd numbers will be the rises for the slopes when I start at the vertex. Okay, so I just want to point out that, right, 1 over 1, 3 over 1, and 5 over 1 were my slopes, all right? And so I was able to find those points, and then I could draw the parabola through those. And then I can immediately find the points on the other side of the axis of symmetry by mirroring those. And I can actually find some points pretty quickly using this technique. So up 1, back 1, then up 3, back 1, and then up 5, back 1, and I land right there. And I can get the rest of my parabola. And actually here I can verify, notice my y-intercept is 8, and earlier we found out that the y-intercept is always going to be your c term. So it does in fact verify and check out. And if I was solving this equation graphically and it was originally set equal to 0, my answers would have been the x-intercepts, which are at 2 and 4, right? And I could solve it like there. So this is the kind of consecutive odd numbers slope trick, I guess is what I would call it, for finding points on a parabola. So let's consider a parabola where it doesn't have a regular shape. So here's one that I got. F of x equals negative 2x squared plus 8x plus 10. And I've previously found the vertex to be the point 2 comma 18. All right. And so based off of this information, I know, let's see, a is negative 2, b is 8, and c is 10. So you would have found the vertex using the negative b over 2a formula to find the x-coordinate. You would then plug the x-coordinate into the function to find the y-coordinate. You could find the y-intercept using c equals 10, so 0, 10 is a point on this, and all sorts of information. But let's just analyze this based off of A. So let's see. Now the absolute value of A is greater than 1, right? So what I mean by that is, right, absolute value of -2 is bigger than 1, which is a true statement. And what does that tell us? This tells us that this is a vertical stretch. So this is growing twice as fast, because the magnitude there is 2, as a regularly shaped parabola. The other thing I know is that A is less than 0, or A is negative, right? Which tells us that this opens down. Okay, so based off of just this information, I'm going to try to get a little graph here. So this one happens to be, that's not even close to vertical. There we go, that's better anyway. 1, 2, 3, 4, 5. 1, 2, 3. And let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oh, I'm not going to fit it, am I? Tell you what. I'll make this 10. And then 2, 4, 6, 8, 18. Right? So this vertical scale is counting by 2's. So let's plot our points. So my vertex is at 2, 18. So 1, 2, up 18 right there. And I know my parabola is opening downwards based off of my previous analysis. And now I want to find some more points. I guess I could figure out that the y-intercept was 10, right? We know that. Using my slopes trick. So what I'm going to do is take my regular slopes, the 1 over 1, the 3 over 1, the 5 over 1, right, these consecutive odd numbers, and I'm going to multiply them by A. Actually, I'm specifically multiplying just the numerator by A, which is -2 in this case. Alright, and it's just the numerator. So what does this simplify to be? So I'll have -2 over 1, -6 over 1, and -10 over 1. So when I plot these points, let's choose orange again. If I go down 2 over 1, right, there's another point. Down 6 over 1, so that's actually going to bring me down to 10. And then from there, I've got down 10 over 1, actually conveniently happening to give me my x-intercepts. And to find additional points, I could mirror this over my axis of symmetry. Right? So here's a point that is 1 away from the axis of symmetry, so 1 unit away in this direction would be another one. This point is 2 units away from the axis of symmetry, so 2 units up. It happens to land on my previously known y-intercept, so that seems to verify that. And then this is 3 units away, so 3 units away this way, over at -1 on the x-axis would be my other point. And now I could draw my parabola. Like so. Something like that, right? So not too bad. And let's see, I want to fit one more example where the value of A is a fraction. So kind of an uglier problem here. I think I can fit it right here. So here's another previously done problem. Let's see, so f of x equals 1/3 x squared plus 2x plus 4. And I previously had found the vertex on this to be -3, 1. So let's see, A in this case is the 1/3, B, the coefficient of the linear term is 2, and C is 4. So based on my analysis of A, I see that the absolute value of 1/3 is less than 1, so that means it's a vertical smoosh. right? Or a horizontal stretch, whichever way you want to think about it. And I also see that 1/3 is less than 0, meaning it is, sorry, that's not true, greater than 0, meaning it opens upward. Okay, so now in this case, I'm not going to use a regular scale. A little pro tip, I guess, that I might say is use the denominator of A as the y scale. Well, yeah, I think that describes what I'm saying. So even if this was like 4/3, I would be using 1/3 as my scale for counting. Okay, so let me draw a picture of this. Let's see. So -3, 1. That's going to be back 3, down 1, and it's opening up. So it looks like I'm mostly going to be in the kind of second and fourth quadrants, or sorry, second and third quadrants. So let's see. So 1, 2, 3, 4, 5. So here's -5. And like I said, my y scale, I'm going to count by thirds. So 1, 2, 3, -1. 1, 2, 3, -2. 1, 2, 3, -3. So every third mark is going to be a whole number. 1, 2, 3. And now let's start plotting some points. So my vertex is at -3, 1. So 1, 2, 3, up 1. Oh, I guess I didn't need to go down so far, but that's okay. Maybe I will have to go higher, though. So let's do that. 1, 2, 3, and 1, 2, 3, 5. So I'm going to move by my slopes. So my slopes for this problem, my regular slopes are 1/1, 3/1, and 5/1. What I'm going to do is multiply just the numerators of these slopes, and that actually is very significant here, by my a value. So 1/3, 1/3, 1/3. So here I'd get up 1/3 over 1. This would be 1/3. I'm going to call this intentionally 3/3 over 1. And this one I'll call 5/3 over 1. And I do realize this can simplify, but since I'm counting by thirds on my scale, it will be easier for it to calculate that. So from here, I'm up 3/3, right? One whole unit. I'm going to move by my slope. So up 1/3 over 1 is right there. Then I've got up 3/3. So currently I'm at 4/3 right here. So up 1, 2, 3/3, putting me at kind of the 2 1/3 spot over 1. So there's another point. And then I'm moving up 5/3. So let's see, I'm at 2 1/3. So 1, 2, 1, 2, 3. 5/3 over 1. And you can see that counting by the thirds for my scale is actually kind of helpful because of the way these slopes happen to land. And notice I get a y-intercept of 4, which agrees with what I would have calculated based off of my c term. And then, of course, I can mirror this, and I think you guys see where this is going from here. That's a sad dotted line, but it'll work. So 2 units away from the axis, so 2 units over here would be 1, and then 3 units away, so 3 units over here would be another 1. And I could draw this, and now this might not look like a smooshed, actually I draw that in blue, don't I? Minus will be consistent. So this doesn't necessarily look like a smoosh that much, because of the fact that, I changed my y scale a little bit. I guess this almost looks like the same measurement, but it's shallower than a regular parabola. So a regularly shaped parabola may look like this. and this is growing at a third the rate. But it is in fact a smooch, and I do in fact have an accurately drawn parabola using this slopes trick. Alright, so thanks for watching my video, and I'll talk to you guys later.